So we were discussing construction of induction motor. So what we have discussed so far is that we have basically two types of induction motor, that is the sleeping induction motor and squirrel cage induction motor. In both the type, the stator winding is a distributed winding. Stator is a slotted structure, and the three-phase winding is distributed in the stator slot. On the rotor, in case of sleeping motor, we have a distributed winding. But for squirrel cage, we have bar winding. And both the construction has their advantage and disadvantages. The main advantage of sleeping motor is that the shorting is through the external circuit. So we can insert resistance in the rotor circuit, and inserting the resistance, we can shift the torque speed characteristic. We can have a high starting torque, and speed control of the motor is also possible by inserting resistance in the rotor circuit. Disadvantage is absent in squirrel cage motor, but in sleeping motor we have a moving contact, the slip ring and the brush. So there will be wear and tear, which will require constant maintenance. So the slip ring motor is not as rugged as the squirrel cage motor, and sleeping motor for the same rating it is costlier than a squirrel cage motor. A squirrel cage induction motor, on the other hand, do not have any moving contact, so it is very rugged, require very little maintenance. However, we cannot change the rotor circuit resistance because we cannot insert resistance in the rotor circuit. It is a short circuit. It is enclosed circuit, cage circuit. So, however, to have a higher resistance during starting can be obtained by properly designing the rotor slot, and depending on that, it is normally, according to NEMA, it is divided into 4 classes: the class A, class B, class C, and class B. The normal design motor is a class A motor here. So if we have normal starting torque around 150% of the full load torque, and maximum torque is 200% of the full load torque. Now, if we have a deep bar rotor or double cage rotor, then what happens for deep bar? And for this inner portion of the bar will have more leakage, flux linkage, so inductance is higher. Here also for the inner lower bar will have higher inductance due to more leakage, flux linkage. Now during starting the frequency is high, that is the supply frequency. So impedance is quite large, the leakage reactance is large at starting. So due to that, the current has a tendency to flow towards the outer area, or in case towards the outer cage. So basically the current distribution becomes uneven, and the result is that the resistance, effective resistance is increased. So we will have a higher resistance at starting. But as the rotor machine gets speed, so the slip decreases, so the rotor frequency becomes very small at running condition. So at that condition, the current distribution will become uniform. So the resistance will be lowered. So high starting torque can be obtained with a deep bar or double squirrel cage motor with a moderately smaller current, because the smaller starting current, because the starting resistance is high. So this is class B. Now class C is this structure. This is also double gauge, but there is a constriction in between. so totally separated cage. So in this case, basically we will have a very high resistance at starting. So we will have relatively high starting torque with relatively low starting current. Starting current is starting current is obtained by the high inherent resistance of the slot. Now for the class D, only this small slot, that is, if you compare with this or this, only the outer cage is there. So basically, this motor will have a high resistance, so it will have a high starting torque with moderate current, but the resistance will be high also during running condition also. So that effect will be that the running slip will be high. Because if we compare the characteristic, so for higher resistance, the characteristic will shift like this. So with higher resistance, the characteristic will shift like this. So if the resistance is high, so running slip will be higher. So the motor will run at a lower speed. Now next one important thing is that the effect of harmonics and rotor and stator slot on the speed torque characteristic of the polyphase induction motor. Now for harmonics, there can be two types of harmonics, the time harmonics and the space harmonics. Now time harmonics are due to the harmonics in the voltage wave. That is, whatever we have derived till now, we have considered only the fundamental voltage wave. But in practice, there will be some harmonics in the voltage wave. So the harmonics in the voltage will create corresponding fields, and so the fundamental, if it rotates a synchronous speed, the fifth harmonic, now for the harmonics, we know as it is it is symmetric wave, so we do not have even harmonics, we have odd harmonics, and the third and triplet frequency are taken care of by the delta connection itself. So important harmonics are 5th, 7th, 11th, 13th, etc. So what happens, the fifth harmonic in the voltage wave will create a revolving field which will rotate at a speed which is 5 times the fundamental speed. So because the frequency of the fifth harmonic is 5 times the frequency of the fundamental. Similarly, now the scalar series. Now some of these harmonics create the revolving field in the same direction of the fundamental, some in the opposite direction. Now the 5th, 11th, 7th harmonics create field that rotates in the opposite direction to the fundamental, whereas 7th harmonic, 13th harmonic will rotate in the direction of the fundamental. So if we find out the slip S5 due to the fifth harmonic slip, so this will be speed of the fifth harmonic, which is 5 times the speed of the fundamental, minus sign because it is rotating the opposite direction, minus the speed of the rotor. Now the speed of the rotor is due to the fundamental only. So fundamental synchronous speed into 1 minus S1, where S1 is the slip of the due to the fundamental, divided by the fifth harmonic synchronous speed. So if we simplify, it becomes S minus 6 minus S1 by 5. Similarly, for the we can derive for the 7th harmonic. For the 7th harmonic, the speed of the field is 7 times that of the fundamental, minus the speed of the rotor, divided by again the synchronous speed of the 7th harmonic. So it will give 6 plus S1 by 7. Now, this way we can derive the sleep for other harmonics also. Now, let us see what is the torque. Now, approximate torque for the fundamental. This is the expression. Now, so we know that the content of the percentage content of the higher harmonic is lower than the fundamental. So, say for the fifth harmonic, if we calculate, say fifth harmonic, it has the magnitude is k times the magnitude of the fundamental, where k is a fraction less than 1. So it will be p into k v1 square divided by, it is the speed of fifth harmonic. So 4 pi 5 f1, where it was f1 only, 5 f1 divided by the impedance. So r1 dash, this root over of this. Now here this reactances are 5 times because the frequency is 5 times. So you can see magnitude of voltage has reduced and magnitude of the inductance have increased 5-fold. So basically the fifth harmonic torque will be very insignificant. That's why while calculating the torque of the machine, any motor, we consider only the fundamental. So effect of harmonic torques due to the time harmonics introduced by the voltage wave is negligibly small. But what is the space harmonic? What is space harmonic? Just to try to distinguish between time harmonic and space harmonic. Time harmonics, but the harmonics due to the harmonic present in the voltage wave. Now, space harmonic is basically introduced because of the distribution of the winding. If you remember the winding distribution, MMF distribution, while we have derived, we have considered the distributed winding with 3 slots per pole per phase. So we have considered only the fundamental current flowing through the winding. So the current I flowing through the winding will create a MMF distribution which is basically stepped in nature, but this angle is very small, so approximately it can be taken as trapezoidal. So this trapezoidal MMF wave can be by Fourier analysis can be shown to be equal to a fundamental plus harmonics. Again, the events are absent because of the symmetry. So we will have odd harmonics. So it can be seen that it is some the magnitude into sine x plus 1 by 3 sine 3x plus 1 by 5 sine 5x and so on. And so consider that all these harmonics are created by the fundamental current only. So the number of poles produced by the harmonic is equal to the number of poles for which the motor is wound multiplied by the order of the harmonic. The time variation of all the harmonic is due to the fundamental only because it is produced by the fundamental current. Therefore, for sinusoidal impressed voltage, revolving harmonic component field in the air gap flux due to the winding distribution revolves slowly than the fundamental. So it will move at a speed lower than the fundamental. So the third harmonic at 1/3, fifth harmonic 1/5 of the 1/5 of the fundamental speed, because if it rotates 1/5 of the fundamental speed, then only it can create number of poles which is equal to 5 times that of the fundamental. So if we try to find, so in general it is 1 by q times the fundamental speed, the rotation of the derivation we have considered. Now So if we consider S5 or the slip due to the fifth harmonic, here say the speed of the fifth harmonic due to slot harmonic, this will be 1/5 that of the fundamental. So twice F1 by P1 was the fundamental speed divided by 5 minus sign because it rotates in the negative opposite direction, minus the speed of the rotor is basically due to the fundamental speed into the 1 minus S1 divided by the again the fifth harmonic synchronous speed. So if we calculate, it will give you 6 minus 5s1. Similarly, so for the secondary frequency due to this fifth harmonic will be this F1 into S5. This will be F1 only because the time variation is basically due to the fundamental. So F1 into S5. So the secondary frequency will be 6 minus 5S1 into F1. Now similarly, if we calculate for the seventh harmonic, the synchronous speed will be 1 by 7 times the fundamental speed minus the speed of the rotor divided by the synchronous speed. Here we have a plus sign because it rotates in the same direction. So it gives minus 6 plus 7s1. So secondary frequency for seventh harmonic will be F1 S7. So minus 6 plus 7s1 F1. Now consider S1 is equal to 0.05. So the rotor frequency, this is the slip of the rotor. The rotor frequency due to the fifth harmonic for 50 Hertz will be, if we put the values in these expressions, then we will see that this is 6 minus 5s1, 6 minus 5s1 into 50, and this is for the seventh, minus 6 plus 7 into s1 into 50. So these are almost equal, almost near to the frequency. Now consider what is the effect, whether they produce a torque or not. Now this seventh harmonic, if they say consider the seventh harmonic. This seventh harmonic will, the speed of the, consider the speed that will induce seventh harmonic field in the rotor. Now the speed of the rotor field with respect to the stator is the speed of the rotor field with respect to the rotor plus the speed of the rotor with respect to the stator. So speed of the rotor field with respect to the, if we consider the seventh harmonic, speed of the rotor field with respect to the rotor will be this by F7 by P7, that is P7 means number of poles for the seventh harmonic, plus as the rotor is rotating at this speed, so plus the rotor speed will be the speed of the seventh harmonic with respect to the stator. So here P7 we would produce S7P1, and for F7 it was F1 into minus 6 plus 7S1 from here. And for this is for the speed of the rotor. So if you simplify, it will give twice F1 by 7P1. So basically we can see that the seventh harmonic field in the created by the rotor circuit will also rotate at the same speed with respect to the stator as the seventh harmonic slot harmonic created by the stator circuit. So as they are rotating at the same speed, they will create a torque, interact and produce a torque. So if we plot, if we will see that if this is the characteristic of the fundamental frequency, then seventh harmonic, fifth harmonic, etc. harmonic torques produced by the slot harmonic also creates constant torque. So for the seventh harmonic, the characteristic, the form of the characteristic is same, but this synchronous speed is 1/7 of that of the synchronous speed. So this form is similar to this, and this is a negative portion. So this is the seventh harmonic characteristic. Similarly, fifth harmonic, the nature will be same, but this this will be in the negative side here. So this mainly we will get negative in this. So the other harmonics also have components, but as the order increases, the magnitude decreases. So higher orders are not of much importance. So the actual characteristic, which should be this one, becomes summation of these three characteristics. So resultant of these three will be, this characteristic will be like this. So there will be a dip here, some unevenness in the torque speed characteristic. So what is the result? Say we have a constant torque which of this magnitude. So if there was no slot harmonic, then the motor should the torque and the motor characteristic intersect here, and the motor operates with this slip. But what happens as this torque cuts the characteristics, say here. Now this is a stable slope, so the motor will tend to operate at this low speed. This phenomena is called crawling. So the motor has a tendency to crawl at a subsynchronous speed. So crawling is usually accompanied by considerable noise and noticeable vibration. However, these space harmonic fields are very small, so normally these torque produced are also small. And this effect is reduced by skewing. We have seen the rotor bars are skewed. The advantage of skewing is that the slot is not parallel to the shaft. It is at an angle. So the linkage of the two ends of the rotor bar are not the same. So that will reduce the slot harmonic torque. So that will reduce crawling, and that's why that is the reason why the rotor bars are skewed. But we should, for design, while designing, designer should be careful about this phenomenon. Then, and there is another effect which is called fogging. Now this is the effect of slot harmonic in the air gap. Now what happens in the both the stator and rotor are slotted. As both the structures are slotted, so and both the structures are moving. So depending on the position of the stator slot and rotor slot, the reluctance of the air gap is changing with time. So even if we consider the MMF to be constant, so the flux is MMF divided by the reluctance, as reluctance is varying with time because of the relative position of the slots. So there will be pulsation in the flux, air gap flux. Now this is pulsating field. Now if this pulsating field can be divided into two rotating field, one backward and one forward rotating field. So there are certain combination of stator and rotor slot which will produce considerable subharmonic torque. For example, these things are quite complicated mathematics, so we are not going into details, but just one example I am showing. That is, so say for example, we have stator slot equal to 24 and rotor slot is 18. Now this combination will possess a reverse 11th and forward 13 harmonic mmf, while for the stator it will create forward rotating 11 and backward rotating 11 and forward rotating 13 harmonic, while the rotor structure will produce backward rotating 13th harmonic and forward rotating 15th harmonic. Now, so both the stator and rotor are producing 13 harmonic. So the stator 13th harmonic rotates at a speed plus ns by 13 with respect to the stator, and the rotor 13th harmonic rotates at a speed minus ns minus nr by 13. Ns minus nr because rotor frequency is proportional to ns minus nr, minus sign because of the opposite direction, divided by 30 with respect to the rotor. So where ns is the speed of the fundamental, nr is the speed of the rotor. These two mmf interact and produce synchronous torque when, say for a particular speed nr, when these two speeds become equal, that is any two harmonics will produce a torque if both of them are moving at same speed. So this is the speed of the stator 13th harmonic, and this is the speed of the rotor 13th harmonic with respect to the rotor. So with respect to the stator, this will be the speed of the rotor 13th harmonic. So it will give that nr is equal to ns by 7. So at this speed, that is when nr is equal to ns by 7, then the rotor 13th harmonic and the stator 13th harmonic rotates as the same speed and interval. So that will have a substantial subharmonic torque. So this phenomena is called cogging. So say for this, at this point, this will be a sharp disturbance here. So this cogging phenomena can be avoided by certain, if we can avoid certain combination of stator to rotor slot. So while designing in the induction machines, some combination of number of rotor and number of stator slot we cannot take arbitrarily. There are certain combination which cannot be taken, and the effect of crawling is taken care of by skewing the rotor bars. So these things, the mathematics behind these calculations are quite intricate. So it is not within the scope of the syllabus, but you do remember the effect, these two effects, cogging and crawling, which is important for induction machine design. Now, next thing I will try to explain is how AC winding is wound. That is, if you remember, you have this studied the DC winding. So in DC machine, we have silent pole structure, that is projected poles. So on this projected pole, we have concentric winding to create the pole. So for DC machine, we can visualize, just visually can see the pole. So if it is a 4-pole machine, there will be 4 projection. If it is a 6-pole machine, there will be 6 projection. But that is not the case for a AC machine, because we have a distributed winding. It is slot, and within the slot there is a conductor. So, and this conductor is connected to form the winding. So here also, I am not going into very details. To some extent, this details will be covered in your design class. I will just give an idea. Say we have a structure which has 24 number of slots and 24 number of conductors. Now we have to connect these conductors to make the winding. Now, if we want to make a two-pole structure and a two-pole three-phase winding, in that case, your Q that is the slots per pole per phase will be, this is 24, pole is 2 and phase is 3, so Q will be 4. So for this two-pole structure, this 4 will be R phase, then B, Y, again R, B, Y. And if you remember the connections, we should have this R phase if this is the direction of the field, then for this B Y phase, this is the direction of the field, resultant field, and the B phase should be in this direction. So that will give, this is R dash, then this is Y dash, and this is B dash. So these are the slots and these are the conductors. So this 1, 2, 3, 4 and 13, 14, 15, 16 can be connected to form a winding. So 1, 13, this 2, 14, this 3, this 15, this 4, this 16, then this is the finish. So this is start, this is finish. This B winding is also connected some way, but connection, this should be start and this should be finish to create that 120 degree displacement. And this is the Y winding. So it will create two poles. So say R phase, we have two poles, this is two poles, this is two poles are created. Now the same 24 slot, if we want to make a 4 pole, then here slot per pole per phase will be 2. So this will be R. Again, this is R, this is R, this is R. This is B, this is B, this is B, this is B. Then this is Y, Y, and Y, Y. So this connection, it is called the mesh winding. This is a single layer mesh winding for the 24 slot 4 pole. Now say this is the red phase. So this, then this one, then this one, and this. This 2 is basically this side, and this one is shown here. So the winding is complete. So similarly, we will have R and B windings. So this will create 4 poles. So same conductor here with 24 slot with single layer, we can create a 4 pole or a 2 pole by just changing the connection. Now, normally this mesh winding is used with small machines. Then normally we will have lab or wave connection, as you have studied in this machine. Here also lab or wave. This is a double layer winding, double layer lap winding. Same 24 slots. So this is the slot 1 and the lower conductor of slot 7. Then 2, 8. So this is the first coil. So this is the next is this coil. This again this is the coil. So this is R phase coil. Similarly, we will have Y phase and B phase coil, and the start position for R phase, this is start, this is finish. For Y phase, this is start, this is finish. For R phase, B phase, this will be start and this will be finish. So this will create a lap winding. This is a 24 slot, 4-pole, double layer lap winding for 3-phase. So there are different types of windings which are used. This I'm just giving the an idea about how the poles are created. So you can see that with same number of conductors, if we change the connection, we can create 4-pole, or here we can create a 2-pole machine. So this winding details I'm not going into very much, because when you design your undergo the design induction machine design class, this will be when we design the winding, it will be understood better. So this is just the explanation how the poles are created, because we do not have projected part for poles. So this is more or less we have covered the induction of the syllabus. Next week I will do one of the few problems, and I will forward all the materials to your common mail. We will have the next class on next Tuesday again, no?